This is Algebra 2, Unit 8, Lesson 4, Fractional Exponents Revisited. Now, we've been working on the concept that the roots, square, cube, or whatever, could be represented by rational or fractional exponents. And we decided that when you see a unit fraction exponents, when you have a rational exponent, and when you have b to the 1 over n, it is the n root of b to the first power. Because remember, this really means, the fractional exponent actually means power over root. So the top number is whatever power is on the exponent, and the root is whatever index is out here on the end. So it can be a square root, it'd be a 2, cube root, it'd be a 3, 4, so on and so forth. Okay, so let's use those ideas to rewrite each expression in the form ax to the b, where a and b are both rational numbers. All right, so 5 times the square root of x. How do we rewrite square root of x as a fractional exponent? Well, remember power over root. The power is going to be 1. The root is actually 2, even though it's not written there. So this is going to be 5 times x to the 1/2. So the a value here would be 5. X to the b would be x to the 1/2. All right, so for letter b, the 5th root of x. Power over root, it would be x to the 1/5 over 4. All right, now we want this written as ax to the b, where a and b are both rational numbers. So what number is actually in front of the x here? It's actually 1. So this can be written as 1/4 to make the rational number, x to the 1/5. So ax to the b. Letter c, 7 over the cube root of x. All right, so written in rational form, the cube root of x would be x to the 1/3. Okay, now how are we going to make this look like ax to the b, though? All right, we'd have to move the x to the 1/3 up to the numerator. So when we move a base and exponent up, what happens to its exponent? It becomes negative. So this is going to be 7 times x to the negative 1/3. So it's its reciprocal. So you do the reciprocal, so it puts it up into the numerator, and it makes it negative. All right, let's do one more. Letter D, 5 over 3 times the 10th root of x. All right, let's rewrite the exponent first. 5 over 3, the 10th root of x is x to the 1/10 power. All right, so I want to write this as ax to the b, so I want rational numbers. All right, so I'd have to move the exponent, base and exponent, up to the numerator, so that will make that 5x to the negative 1/10 over 3. So 5/3 I can write as a fraction, x to the negative 1/10. All right, so now let's look at some more rational exponent connection to roots. Now, we know that if it's m over n for the rational number, b to the m over n is equivalent to power over root. Power over root. And we learned the other day that it doesn't matter if we do the power first and then the root, or the root first and then the power. It doesn't matter. All right, so rewrite each of the following power root combinations of rational exponent in simplest form. Okay, so x to the 7th, the square root of x to the 7th. Well, we can rewrite this as x to the 7th to the 1/2 power. All right, so power to a power, it's going to be x to the 7 over 2. Okay, power over root. Okay, x to the 6th to the 4th root of x to the 6th. So that would be x to the 6th to the 1/4 power. Power to a power means you multiply the exponents. It's x to the 6 over 4. All right, now that reduces. 6 over 4 reduces to 3 over 2. Power over root. Okay, now what if we had the square root of x raised to the 6th power? Well, let's rewrite this as a fractional exponent. The square root of x is x to the 1/2 to the 6th power. Power to power means you multiply the exponents. 1/2 times 6, which is 3. So it's going to be x cubed. All right. The cube root of x to the 10th. Well, the cube root of x is x to the 1/3 raised to the 10th power. All right. Power to a power, you multiply the exponent, so it's 1/3 times 10. Put 10 over 1 if you want to. It's going to be x to the 10/3. Okay. So we can leave them just like that. So it doesn't matter if you do the power first and then the root, or the root first and then the power. It doesn't matter. You get the same answer. All right, but it's still power over root. Okay, let's try exercise 3. If f of x equals 10x to the 3 halves minus 24x to the negative 1, which of the following represents the value of f of 4? Find the value without the use of the calculator and show the steps in your calculation. All right, so f of 4 means we take each x and plug in a 4. So 10 times 4 to the 3 halves minus 24 times 4 to the negative 1. So there's my input, putting in the 4. All right, what is my output? All right, so we have to evaluate the exponents first. All right, now 4 to the 3 halves. What does that actually mean? All right, what root are we doing? We are doing the square root because the 2 is on the bottom. It's the square root of 4 and then cubed. Now, we can either cube it first and then do the square root, or we can square root it first and then do the cube. I'm going to square root it first and do the cube afterwards. All right, and then 24. What's 4 to the negative 1 rewritten as? Well, positive, to make it a positive exponent, we have to use its reciprocal, so it would be 1 over 4. All right, so 10 times the square root of 4 cubed. The square root of 4 is 2. Cubed. 2 cubed is 8. Okay, now if we did 4 times 4 times 4 first, it would be 64. The square root of 64 is 8. You can do that too. All right, and that's going to be minus 24 times 1/4. 10 times 8 is 80. 24 times 1/4 is 6. 80 minus 6 is 74. So it should be number 4. All right, let's look at the next exercise. Which of the following is not equivalent to x to the negative 7/3? All right, well, let's rewrite this and see if we can use our rules for exponents and if we can rewrite this. So how could we rewrite the negative exponent? Well, we could rewrite it as 1 over x to the 7/3 to make it positive. So it could be equivalent to this one. Okay, now how do we rewrite the cube root, the 7x to 7/3? It is the cube root of x to the 7th. So we could rewrite it as 1 over the cube root of x to the 7th. Okay, so that works. Now that would be this one right here. All right, so it could not be number 2. So it could be there. Now, could it be this one? Well, let's see. It will be, because we can rewrite this as power over root. It would be the cube root of x to the negative 7th, which you can rewrite as the cube root of 1 over x to the 7th. So that would work as well. So that one does work as well, so it would have to be number 2, because the root and the power are backwards. All right, now fractional exponents play by the same rules or properties as all other exponents. It is, in fact, these properties that can justify many standard manipulations with square roots and others. For example, simplifying roots. Now, we only consider a square root simplified when all of its perfect square factors have had their square roots evaluated. All right, so when we simplify square roots, we look for the biggest perfect square that goes into the root, and then we take its square root. So the reason that comes from the exponent property here, ab to the n. The exponent property says the outside exponent applies to each of the inside. So this is going to be a to the n, b to the n. All right, so if we write square root of 28 in factored form, with one factor being the large perfect square divisor, what's the biggest perfect square that goes into 28? It would be 4. It would be square root of 4 times the square root of 7. So we know that can be rewritten with exponent form. So we could write 4 to the 1/2 times 7 to the 1/2. All right, so we can write it as 4 times 7 raised to the 1/2. All right, so if we use this property, it's the square root of 4 times the square root of 7, or 4 to the 1/2 times 7 to the 1/2. 4 to the 1/2 is the square root of 4. 7 to the 1/2 is the square root of 7. 2 times the square root of 7. So you can do it both with exponents, or you can do it with radicals. So if you want to generalize that rule, the square root of a times b is the square root of a times the square root of b. That's why we can split it into 4 times 7. All right, so the n root of a to the b can be the n root of a times the n root of b. So you can split it up into separate ones. All right, so let's do some simplifying of square roots. We've done this before, so let's see if we remember, and then we're going to look at other roots besides square roots. Okay, now let's see if we can simplify the perfect square roots. Usually what you want to do is you want to split them into a list of perfect squares and times the non-perfect squares. Okay, so I want to split this into two groups, perfect, non-perfect. Okay, so what perfect square goes into 18? The biggest one would be 9. 9 is a perfect square, 2 is not. 9 times 2 is 18. All right, now, x to the 4th, is that a perfect square? Yes. Even exponents are perfect squares. Are perfect squares. So that is going to go in my list of the perfects. All right, so this is the perfect, and these are the non-perfect. So once I've got them split up, the square root of 9 is 3. The square root of x to the 4th is x squared. And this is the non-perfect squares. It just stays like that. All right, so making my list here, the square root of 200x to the 5th y cubed. Perfect, non-perfect. 200 is 100 is a perfect square times 2. X to the 5th. What's the biggest even exponent that goes into x to the 5th? It would be x to the 4th. So it would be x to the 4th times x. And then y to the 3rd would be y squared times y. Perfect, non-perfect. All right, so these are all the perfect squares. The square root of 100 is 10. The square root of x to the 4th is x squared. The square root of y squared is just y times the square root of 2xy. And we're done. There we go. Okay, let's do one more. Perfect squares. Non-perfect squares. 147. Well, that one is 49 times 3 gives me 147. Perfect, non-perfect. X to the 9th. The biggest even exponent that goes into x to the 9th would be x to the 8th times x. And then y to the 4th is a perfect square because it's even. It would go over here. Take the square root of all of these. The square root of 49 is 7. The square root of x to the 8th would be x to the 4th. We just divide the exponent by 2, power over root. And then y to the 4th would be y squared. And then times 3x. And there we go. All right, so we can extend the simplifying process to include cube roots and higher roots by simply extending our thinking. All right, now notice here, we would go, one group would be the perfect root. Times the non-perfect. But instead of using squares, we're going to use cubes and fourths and fifths. All right, so let's deal with cubes. It would be helpful if we knew what some of the perfect cubes are. Usually if you know the first 5 for the perfect cubes, those are the ones that are used the most often. All right, so 1 cubed would be 1. 2 cubed, 2 times 2 times 2 is 8. 3 cubed, 3 times 3 times 3 is 27. 4 cubed would be 4 times 4 times 4, which is 64. 5 cubed is 5 times 5 times 5, which is 125. So there's the first 5 perfect cubes. So that should give us a start. All right, so if I'm going to do the cube root of 16, I want perfect cubes and non-perfect cubes. All right, of these numbers of the perfect cubes, which one goes into 16? It would be 8. 8 times 2. What is the cube root of 8? The cube root of 8 is 2. 2 times 2 times 2 is 8. 2 times the cube root of 2. Done. All right, perfect cube, non-perfect cube for 108. Which one of these numbers goes into 108? It is 27. 27 goes into 108. It would be 27 times 4. The cube root of 27. 3 times 3 times 3 is 27, so the cube root of 27 is 3 times the cube root of 4. Don't forget, this is the cube root of 4, not the square root of 4, so it doesn't simplify any farther. All right, let's see if we can work out the rest of them in class the next day.